This example is similar to before. And you got it in my slide. So I will skip this, okay, because you can read it in the slide. Just example how to find the eigenvalues and eigenvectors. Okay. So we'll take a breaks. Okay. For 10 or 15 minutes. Is this okay?
Yes, sir.
Okay.
Yes, sir.
Take a break. Okay. Good. Okay.
Alo, nhờ tí anh em lắp điện nhé.
Alo, xong đi học rồi.
Đã cài cái SVNet chưa?
Cài ơi.
Ai có vấn đề gì không? Vào cài hết đi, mở điện thoại ra, tải cái SVNet đi về đi, cô Ngân không cho đi học đâu, cô nhắn tin đấy.
Làm bên đây đi học.
Cài xong thì cũng có được đi học đâu ấy.
Xong rồi đưa. Tập nhật xong hết rồi.
Để xem nào, để nhắc lại.
Em điền đầy đủ thông tin các thứ vào để được đi học ấy.
Tên đăng nhập là mã số sinh viên nhá, mật khẩu là từ 1 đến 6. Ai làm xong khảo sát thì nhắn tin, chụp màn hình và gửi tao nhá. Anh em lấp điện nhá.
Phải chụp à?
Làm xong rồi nhưng mà chưa chụp.
Làm xong rồi chụp màn hình gửi tớ nhá.
Nó thoát mẹ rồi.
Thoát rồi phải làm nào, vào làm lại à?
Và làm lại tí.
Không cần làm lại đâu, vào là có cái dấu tích xanh ở đấy rồi.
À thế hả?
Cái gì đấy? Cái dấu tích xanh là được ấy.
Tí tiếc cái gì ở đây hết.
Cái gì đấy anh em? Gửi bài gì đấy?
Còn kiểu viết thường không dấu và không được cắt đi.
À, cái SNS à?
Đây tao sẽ chụp cái chữ nó ghi là bạn đã trả lời xong câu khảo sát cho bạn Đức xem.
Ok.
Đây.
Không mày đâu.
Chả nghe được cái gì cả.
Có cần inbox không bạn Đức?
Gửi vào nick Facebook thì gửi vào nhóm làm gì mấy cái đứa này.
À thì là phải nhắn tin riêng à? Inbox không kín à?
Tin riêng nó mới kín.
Ok. Kín ngay. Con gái rượu thầy Puta là đứa nào ấy?
Mày chứ còn ai ở cha?
Ô, đứa nào lại đổi thành cái đấy rồi? Tao tưởng cái tên đấy trước là dành cho con Tuyết mà. Tuyết quân đội. Đổi được nửa năm nay rồi. Cái thằng Linh đổi phải không?
Mời một người lớp điện vừa gửi ấy nhá. Mọi người gửi ebook riêng nhá, đừng có gửi lên nhóm, không tổng hợp được đâu.
I don't understand.
Okay, are still there, everyone? Okay, good. Now for example, so please find yourself eigenvalues and eigenvalues of this matrix, please.
Mạnh mẽ đến nụ cười lên em như chưa quên đi sắc xa.
When you finish your solution, please.
chậm chậm mơ đi không.
You finished?
And I heard that song.
Are you finished?
Just doing, sir. Please wait.
Okay. Okay, no problem, no problem.
I post it on Zalo, sir, but I don't
Okay.
know it's correct or not.
Mm-hmm. Then this you got a number 3, 2 times. Okay. So we have number 3 square multiplied by number 5, number minus 5. I'm not sure, yes, because I didn't do this. I just make this. And when you are doing in by hand, I check it by MATLAB code.
Yes, sir.
Okay, I will see this. Okay, I think that you had the correct answers about this, about the eigenvectors. Okay, and how about the eigenvalues? Look at this. Okay. Eigenvectors. This is it. Okay, everyone check with this, please. Any ideas, any other solution, please? Is there any other solution, please? Everyone?
Sir,
Yeah.
can you check about the number, the lambda 1 when lambda equal 3?
Yeah.
Because I just see this V1 just have a one solution because maybe it got 2. Can you check this?
I do not understand. What do we mean? What do we mean about it?
When lambda equal 3, sir?
Yeah.
Because this is a repeated root.
Yeah.
So I think this will have got something like 2 of V1, something like this.
Okay. Okay. Yeah, because this is a repeat. Okay. So we have to reconstruct because this is the lambda V1. You in this case you find, I don't know whether or not you find V1 correct or not. Okay. I don't know. But this is because we have this similar V1 because we got the lambda 1 square. Okay. So actually we've got 2 of this.
And how to do this, sir? How to do this?
Okay, I will show you later. I will show you now, but I have to first. I have to check the solution is correct or not first, because I didn't prepare this. Okay, I just have no solution here, so I have to check. And I do not do this by hand, and I check this with the MATLAB code. Okay.
Okay.
Your
So I
voice
would like to check
repeating,
with
sir.
other. Sorry.
Your voice repeating.
I think that is still turn the microphone, so turn it off. If you would like to talk, just turn it and on, and when you finish, turn it off, please. Please check this because I have some different I have a different solution from MATLAB code. So please check this. Do anyone have a different solution, please? Nobody answer?
Sir?
Yeah.
How can I check the eigenvector by MATLAB code?
Okay, I will show you now. Just wait. Okay. Because I need somebody else to have the solution, but I didn't hear anything from other. So do we have any more?
No, sir, because I just confused about the repeated word. So please solve.
Yes, I know. Just why I give this solution, because it related also the to the Jordan or block. You see, when you have the repeated solution like this, I will show you later about how they are related to each other. Okay. Because I said I didn't check this with the hand, so I checked with the MATLAB code. So I'll show you how can we check this with MATLAB code. Okay, and here, this is a MATLAB code. If you want to check eigenvalues and eigenvectors using MATLAB, okay, so you can use eigen here. The command for this in MATLAB is eigen A. Okay. So in MATLAB, you make A. In this case, you got A equal. You want to check this solution, you put A, A4, 0, 1, okay, 2, 3, 2, and 1, 0, 4. Okay, and then you put V and D. V is vectors, eigenvectors. D is eigenvalues. Okay, and we check with this eigen A. Now, if you have the computer with you, please check with this.
Can I share my screen?
Okay, of course. Okay, let me. Yep. Now, please.
The host disable. I don't know, sir.
Yep.
They not allowed me to share my screen.
Okay. Now let me set this. Okay, you can see now.
Here, sir.
Yeah.
I put vector A.
Yeah.
Here. Right here, sir.
Yep.
And I found but I don't know how to understand it, read it.
Okay. You see that you have the eigenvalues. You can find the eigenvalues here, but because this is because we got eigenvalues. We have 3. Okay, and you have for example, for V1 we got 1, 0, 1, for example, or alpha 1, 2 alpha 2, and 1 alpha 1, for example, like this. So we can put any number you want. Okay.
Yes.
And for the D, this is if you look to the columns, it contain the column vectors of the eigenvalues. Okay. You see in my slide. You see in my slide, I put the V is the whole the column of V are the eigenvectors.
Mhm.
Okay, and the diagonal matrix D is eigenvalues.
Here, sir.
This D, yes,
Yeah.
this is eigenvalues.
How about this? How can I read it?
V, the columns are the eigenvectors, also the right eigenvectors. V for vectors, okay,
Okay. Yeah.
and D is eigenvalues. It in the diagonal matrix D. In the main diagonal, we see that this is a eigenvalue. We have 3, 5, and 3.
So it means here we have 3 vectors.
Yeah.
And one here, and the second
The
vector.
column vector. Yeah. So
Is
in
alpha.
this is this you can see alpha, 2 alpha, and alpha.
Okay.
Yeah.
And this one minus
This
alpha.
is yes, 0 and alpha.
Okay.
It's something like this. Okay.
Okay, sir. Thank you, sir. Maybe I stop
Okay.
saying.
Okay, just stop there. Like this. Okay, so for the MATLAB code also, I also, and I don't know, I put it here on. I pull. Okay. Now I will show it later. I will show you how to check with the Jordan form, and how can we find Jordan form, and how can we make the diagonal form for the problem you got before. Okay, because it's really helpful if you got the diagonal form, because I said you can find the solution easily if, because you have to find xt equal e at x naught. So this is you have to find this, but if A got A in a diagonal form, then this will be easy to find. Okay, but first we will look to the another topics about the relation between eigenvalue and poles. This eigenvalue is related to the A matrix, okay, system matrix, and the pole related to the, you see, it related to the this is a characteristic equation from the transfer function. Okay, for example, like this. You already know that if we got A, B, C, D, it's this representation, you can find Z. Okay, this is a transfer function of the system ZS by this equation. Okay, and how we have to find this. Okay, this is a matrix, like, okay, maybe A prime minus 1, where A prime equals Si minus A. Okay, so we have to find the inverse matrix like this. You have to find adjoints of this. Okay, and actually, if we would like to find the inverse matrix, it is A prime inverse 1. This equal to, here see, adjoints of A prime divided by determinant of A prime. Okay, and you already know that we have to make sure that this should be different from 0. Otherwise, A prime called singular. This is singular matrix. Or they have the rank of A different from N. If A belong to the N, so the rank of A is different from or smaller than N. Okay, Okay. Well, we already, okay. Okay. Then we can rewrite this. We already know this, so we can rewrite this by this form. If we this inverse. Okay. And this is the, if we take this one, it equals 0. Then this is the pole. We will find the pole of transfer function because this is transfer function. Okay. But lambdas, the determination lambda I minus a equals 0. This is pole, we got pole, but it also the eigenvalues. When we find the eigenvalue, we have to show this. Okay, as the previous one. I hope that you still remember this. I don't repeat this. So this means that the pole of transfer matrix are the same as the eigenvalues of the matrix. Okay, so if you find okay, A, B, C, D, we have A, B, C, D, and you got also GS equal, for example, where we have before S plus 2 divided by S plus 1 plus square S plus 3, like this. Okay, so this is a pole of this, and this is pole of this. But the pole of this is also the eigenvalues of the matrix A. Yeah. Okay. So this is a relationship between the eigenvalues of the matrix, the system matrix, and the pole of the system. They are same. Okay. Again, the pole of the matrix, sorry, of the transfer function is the eigenvalues of this matrix. Okay. And if we got the matrix A prime in diagonal sign, and we can represent it like A equal lambda 1, 0, 0, 0, lambda 1, 0, 0, lambda 1. For example, if we are more. Okay, 0, 0, 0 here, and lambda 1 here. Lambda 2, lambda 3, lambda n. Okay, if we got the diagonal form, then we can represent this is eigenvalues, and also this is also the pole of the system. Okay, and the next. So at this point, remember the pole of the transfer matrix is the eigenvalues of the matrix. And now we will see the transformation of system variables. Okay, you already know that for one system, we have several ways to represent the state or represent state space of the system. Well, we got one system with different state space representation. We can put it in the controllable form, or maybe observable canonical form, maybe diagonal canonical form, or Jordan form. This is depends on what we want to present. Okay, for example, if you got, for example, you got the circuit like this. Okay, or like this. Okay, for the same circuit, and we got here, see the current I, and here is voltage VC, like this, VS, and this is R1, this is L1, and this is C1. Okay. And now we assume that we got the two variable here is I and VC. Okay, but we can represent this system with the different variables like this. We would like to have two variables. We find two variables is i's, the current I here, and this is R1, this is L1, and this is the C1. But we have the first variable i's, and the second variables here we have to find here VL. So in this case, the state variable can be I and VC, and in this case we got I and VL. Okay, two different ways to represent the same system. And now we see that because with the same system we can transform state variable from one to another. Okay, so how can we do that? And when we do that, we prove that when we change the state variables, but the eigenvalues or the pole doesn't change. Okay, and you can do that like this. You can prove that like this. Okay, now the choice of set of state variables like I or VC or VLs. Okay, to represent the system is not unique. Okay, for the same system we can choose the set of state variable, the different set of state variables. It is possible to define the infinite number of different representation by transforming state vector by linear operators. We got this, the definition or concept of linear operators. Okay, now assume that the system is described by state vectors x and the new set of state vector x primes. Okay, meaning x primes with a like x here is defined by this, and here x prime is defined by this. Maybe it's not correct. We can choose another way, but I assume that we have two different for the same system with a different state variables. Okay, and we'll have the relationship between this, of course, because the same system, then they have the relationship. Okay, so in this case, we can see that x is the first set of state variables, and here we got the second set, and this is linear operators P. Okay, so we can rewrite x by P x primes. It's something like this. And we assume that P is non-singular, or determinant of P is different from 0. We assume that. You have to find this. Okay. So we assume that we change from x to x primes by this. Okay, and of course we can rewrite, if we want to rewrite this, we can rewrite this x prime equal to P minus 1 x. Okay, this is a new one, and this is a O1. It doesn't matter because we can find the P, and of course when we find P or P minus 1 is easy because we make sure that it exists because we assume that determinant P different from 0. Absorb P divided by determinant P. Okay, now assume this. So we assume that we have x dot equals AX, the homogeneous only for system matrix. Or we assume that the input is 0, U is 0. So we only consider the characteristic equation. Okay. Okay, so x dot equal to, okay, so we have here x dot equal to p x prime dot. And we assume that x prime is, of course, equal to this. Okay, so in this case, we got, or we can put x dot equals like this, equal to ax. Okay, and x here equal to px primes. Okay. So in K we this K also considers K x dot equal to ax plus bu. It doesn't matter. You can put it use here. It doesn't matter, I think, because we got is this one. Okay, so we just replaced x by p x prime. So we have ax plus bu. Then we got this one. Even you can remove use, doesn't matter. Okay. So here we got P and AP primes and BU. So now you multiply both sides by P minus 1. Okay. So we got this is a P minus 1 P X dot primes. Then here in the left hand side, right hand side, we got P minus 1 AP X prime plus multiply P here, P minus 1 B use. Okay. And this is, you see, this is an identity matrix. Okay. Multiply x prime, it doesn't matter because this is a unitary matrix. So you can find this one. So x prime dot equal to this. Okay. And now we group this with this. Okay. And this with this. Okay. And also, this is a y equals cx, cx equals c. Remember, x equal to p, x prime. So we just put c, x, but here, c, p, x prime, du. So this is output equation. Okay. So now we got this is, I can rewrite this x prime dot equal, this is a primes. Okay, we don't need to put this anymore. So I put it as a primes, x primes plus b primes use. Okay, we change from x to x primes when we got this. Then we got the characteristic equation is determinant of lambda i's minus a prime equals 0. So we see whether or not the eigenvalue here, lambda I, of the new system with the same system with the difference state variables. And we check with the lambda here. Okay. And here we do this. This is the lambda I, and a prime is here. A prime is here. Okay, and it is 0. And also we can, okay, lambda I in identity matrix, we can rewrite identity matrix by any non-singular matrix. Okay, for example, I can be written in this form, I equal Q minus 1 IQ. Any non-singular matrix can be written in this form. But in this case, we put P minus 1 P. Okay. So we got lambda I will be lambda P minus, of course, we have put I here, but everything multiplied by I will be I. Okay, will be there, will be unchanged. So I equal P minus 1 I P or P minus 1 P. Okay, so we'll put it this form, and here we have also P minus 1 AP, P minus 1 AP. Okay, and it equals 0. Okay, so lambda here is, you see lambda here is scalar number, so we can put it here. Okay, put it in lambda here. Okay, and then we take P minus 1 outside, and then we because we have the same this and the same P. Okay, so we'll put P minus 1 is to the left hand side. When inside we got lambda I, and in here in the second term we got minus A, and in the right multiple we got P, and it equals 0. Okay, and remember that we got determinants of A multiply B multiply C equal determinants A multiply determinant B and multiply determinants C. Okay, so this is, we have to calculate this, calculate determinant of this, and 3 passed. Okay, so we have to find determinant P minus 1, determinant of this, and determinant of this. Okay, but assume that P is not singular, then determinant P different from 0. We got it here. Okay, so this part also, this also different from 0. So this is not different from different from 0. This is different from 0, and it equals 0. So in other words, it should be 0. Like this. Okay. This means that when we show this for X primes for this equation, but they got the same characteristic equation. And because they have the same characteristic equation, it has the same, sorry. Okay, so both of them have the same characteristic equation. This has the same characteristic equation for the previous one, or in other words, they both have the same characteristic equation. This meaning that the characteristic equation and hence eigenvalue lambda I of the model response component, this is for the first case, are invariant under the linear transformation of the system state variables. We can change state variables, but the eigenvalues or the root of characteristic equation doesn't change. It do not change. Okay. Remember, this is a reason. The quantities are properties of the system itself and are not affected by the choice of state variables. Okay. This state variable used to describe the system dynamics. Okay. Meaning that, again, meaning that we have the same system like this. If you would like to change state variable, it doesn't matter. The system still itself, and the property of the system doesn't change. Okay, so that reason why when we can change from state space representation from this to another. Okay. 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 So this is the conclusion of transformation from the state space. In the state space representation, you can change the set of state variable from one to another, and doesn't matter, doesn't affect to the system. Okay. Okay. Now come back to this example. I would like to inform you that in case you got the eigenvalues and eigenvectors of a system, you can also find Jordan's or you can find a diagonal form for A. Okay. And we assume that if you find the vectors, the eigenvectors of the system, okay, then you can find this, the Jordan form of this. Okay, let me check with the MATLAB first, and I show you now. Okay. Okay. They can prove that if you find the in the previous case, you find the eigenvalues by using V, D, eigenvectors, this is eigenvector, and then the diagonal, the D for diagonal of the eigenvalues. So V now become the matrix with its columns is the eigenvectors. Okay. And in previous parts, if you use the MATLAB command, you see that V equal 3, 0, 0, and we got next we have 0, 5, 0, and 0, 0, 3. Okay, with the MATLAB. Okay, you return in the MATLAB, and you can find the A prime, or you can find A. We can find the diagonal form of A. Okay, using this. Okay, I will denote it by AD. Okay, it equal V minus 1 A V. And you know that this is a linear operators V, the linear operators, and you apply this, the characteristic equation, the solution of characteristic equation doesn't change. Okay, and property of the system doesn't change, but we change from, okay, it's not diagonal form into the diagonal form. Okay, you can check this with the MATLAB code. Okay, for example, you got A here, V and D, then we, for the MATLAB command, you can find this like, okay, AD equal inverse V, and we put inverse V multiply A multiply V. And now check with the solution, please. Check yourself. And of course, you will find this is also D.
The MATLAB code show a little difference.
Why? What do you got?
I don't know why.
Just share with us, please.
Okay. Here's the value of
No, it's not D. V, please.
V.
V. This V. Okay. You see that? And I said this is also D. Okay. This is D matrix.
Okay.
So what does this mean?
It means the eigenvalue, like something never change in the system.
Yes. Okay. But also it means also that, okay, in this equation, maybe it's not V, but you see that, okay, in 0K, we got the A, the matrix A, and you can find a D if you can find any Q matrix. A Q's, okay, will be transform A into the diagonal form, okay, in 0. But also we all know that Q is one of Q, because it maybe when we find Q's, but the Q's is eigenvectors. This is the matrix of the column, with the column is eigenvectors of A in this case. Okay. So it's something that we emphasize that even when we change this into the diagonal form like this, the eigenvalues, it doesn't change. It is still because this is characteristic of this equation or the property of the system. Okay. We will come back to this later. And because the next chapter, because in the next chapter, in chapter 4, we will see that we need some canonical form for the problem of pole placement. We'll call this a pole placement methods. Okay. We will see this. I will finish my lecture today in here, but I will guide you a little bit about this chapter 4 and why we need the chapter and why we have the chapters and what the chapter is for. Okay. So in next chapter, in the next lecture, I will show you the methods, the first methods for the state space representation problem when we call pole placement methods. And we got the problem like this. Assume that you got a system like x dot equal to ax plus bu. And if you find the eigenvalues of this system is lambda, and you can find this, the lambda also is the poles, okay, or poles of the system. And we find that some poles in the left-hand side, for example, like this, it's okay, it's good, because the system is stable, okay. Do you still Do you know when the pole in the left hand side is stable? You need to review this, okay, in the system one, okay, because we got, when we show the problem of x dot t, we will see that this is C1 E minus or C1, okay, is like this. E1 lambda t is something like this. It is first order. So if lambda is negative, then the system will be stable. But if lambda here is positive, then when we t increased, this also increased up to infinity. If we have the pole like this, the system may be good, but the requirement is that we have to move this into the left-hand side to make the system more stable. Okay. Even when God response of the system is slower, but we assume that in this case, we got the system have the two pole like this and one pole is here. So the system is unstable. And now this requirement is that this system is unstable. And the problem here is that you have to design a controller K that move this from lambda 1 or pole P1, P2, and P3 up to P1 prime, P2 prime, and P3 from here. Okay, you have to move this. Or in other words, you have to place the pole of system to this position, to this position, or to this position. So this why they have this method called pole placement methods. Okay, and we will do this in my next lectures. Okay. Okay.
Yes,
Any
sir.
questions
Yes,
so
sir.
far? Okay. Any questions?
No.
Okay. Read this chapter first at home. Okay, and then I will be back with you about this. Okay. So I think that we have one student still missing. Okay, and do you know who to listen today? I don't need to check. Otherwise, I have to check one of you. Bùi Thái Anh, please.
Yes, I'm here.
Okay. Nguyễn Quang Anh,
Yes.
Phạm Tuấn Anh,
Yes.
Văn Đức Chiến,
I'm here.
Phạm Bá Cương,
I'm here.
Nguyễn Việt Cường,
Yes, sir.
Phạm Mạnh Cường,
Yes, sir.
Đặng Thùy Dương. Đặng Thùy
I'm
Dương.
here. Yes.
Okay, good. Lê Quang Đạt,
Yes, sir. I'm here.
Đỗ Văn Đức,
I'm here.
okay. Nguyễn Thế Đức, okay. Nguyễn Văn Hà,
Yeah.
Vũ Thanh Hải,
Yeah. Yes.
Đặng Thị Minh Hiền,
Yes, sir.
Nguyễn Thị Thu Hiền,
I'm here.
Bàn Phúc Hiếu,
Yes, sir.
Hoàng Văn Hiếu,
Yes, sir.
Lương Công Hiếu.
Yes, I'm here.
Okay, good. Phan Trung Hiếu.
Yes, sir.
Okay. Trần Đức Hiếu.
I'm here.
Okay, I saw you. Lưu Văn Hoàng.
Yes, I'm here.
Okay. Đỗ Quang Huy.
Yes, I'm here.
Okay. Nguyễn Quang Huy.
I'm here.
Okay. Nguyễn Xuân Huy.
Yes, I'm here.
Okay. Nông Văn Huy.
Yes, sir.
Nguyễn Nam Hưng. Okay, no. Nguyễn Văn Hưng.
Yes, sir.
Okay, so we missed one. When Nam Hưng is not, I think this is not participant in this course anymore because I checked 3 times absent.
Sir, I am Trần Tuấn Minh.
Okay, no, I just checked for one missing. Okay, and then one missing now. Don't worry, Okay. Any questions? Any more question, please?
No, sir.
If you have no question, I will finish my lecture today and see you next time.
Sir,
Okay.
I'm Trần Tuấn Minh.
I know. I just checked and I found one missing. Okay. I know that we have one missing.
Yes, sir.
Okay. Only. Okay. It's not used. Okay. Thank you very much.
Thank you.
Okay. Okay.
Goodbye.
Thank you.
Thank you, sir.
Goodbye.
Hi, teacher.